Mic on? Great. Good evening, everybody. Good to see you. Was there any snow out here? I came up from Virginia Beach and it was snowing, so good. Nice to see you, Hardy. You guys are becoming New Englanders. Look at this. It's fantastic. Got your coats on, your scarves. Pretty exciting. Well, tonight, unfortunately, is going to be our last session for now, although we might be doing to be continued with other parts of the universe if we can press gang Johnny into some other time as well. But next week he's going to be away, and so we're going to compress things kind of like a black hole into today's one session. So let me open with a word of prayer and hand things over to our master of the universe. Heavenly Father, we thank you so much for this opportunity to take a break from our day, and at the end of the day to just sit in your presence with one of your servants, to be taught about the beauty and the majesty and the wonder of your creation. Lord, forgive us for living so many hours of our lives with our necks bent over and our eyes focused on little things. Teach us, I pray, tonight to lift up our eyes to the hills and to beyond the hills, from whence our hope and our help comes from. In Jesus' name, amen.
Okay. Yes, you can hear me now. All right. So first of all, I'll give you my grade from last week, which was an improvement. So I got a 90 and a 95, so I'm feeling good. What's that? That's why I didn't get a good grade, the perfect grade. Last week you could not hear me, so now I'm going to try to project more, and I moved the mic up, mostly. Okay? So, are we ready for tonight's discussion of the sun? So, like the preacher said, I unfortunately cannot be here next week to finish out. So we're going to miss out on some of the things we're going to talk about then. But I'll try to kind of wrap it up as best I can tonight with some of the stuff you'll see here. And we're going to talk about the sun in particular. Okay? All right, Jason. So first off, review of 1 and 2, weeks 1 and 2, right? First time we kind of set the stage from a biblical perspective of should we even be doing this, right? And how it should look and what Adam and creation all went through, right? We did the whole thing with the adding 0 to the end of numbers. Don't forget, don't do that. That's not what you're it's an order of magnitude, and it means a lot more than adding a 0 onto the end of a number, okay? Week 2, we looked at it all, the universe, everything. Stuff close in, stuff far away, effectively. God lets us see that, but he kind of put up a barrier for you. You can look, but you can't touch for a lot of that stuff. Amazing anyway, for what we can see. Tonight, we talked about stars in general during the universe part. Tonight, we're going to focus in on one in particular, the sun, okay? Any questions for the first 2 weeks that you got to get off your chest before we get going? Okay. All right, Jason, it's another one. So the sun is our star. We know exactly actually when it was made and what it was made for. God actually told us that, right? Right here in Genesis. And God made the 2 great lights. One for the day and one for the night. And he made the stars also. And it was on the 4th day, right? Which is a little odd because he created the plants and stuff on the 3rd day. He can create them however he wants. And then there's actually a lot of verses about the sun in the Bible, and a lot of them are because of the clockwork nature of the sun comes up and it goes down every day at the right time, right? And here's a verse from Ecclesiastes that gets to it. So, of all the magnificent and wonderful things God made, this one is the one that is an enigma to me. It's just special. Go ahead, Jason, and we'll talk about why. So here's just a few pictures of the sun. It's hard to look at with your naked eye, right? It will hurt you, right? So we developed a lot of different kinds of filters to look at the various kinds of light that comes off of the sun. The one in the middle is the one that is most often seen. It's the hydrogen alpha line, I think is the name of it. But it allows you to see the sun, and it allows you to see the prominences and the loops of magnetic fields off of it. Also lets you see those dark areas, which are called corona holes. And you can tell a lot from the sun from that. The one on the top right is for just seeing sunspots. So you can count the sunspots and tell a lot about the sun. And they map these things. People do it by hand and by automation every day. And we have records of these things going back into the early 1800s, actually. The one on the right is bottom right is from a network of sensors. There's, I think, 8 of them around the globe that NASA runs. And you can actually look at the light coming from that and tell what's happening on the other side of the sun through the seismic activities. And it's just, it blows my mind that they can do it, but they do it, and it is phenomenal. The lower left one is a zoomed in area on a sunspot. And what they are is where the magnetic fields go back into the sun, so they're cooler, actually, than where it's coming out. So it creates a darker spot. Not really dark, but compared to the surroundings, it's dark. Don't be fooled by the size. Again, we got to kind of set our stage and standard, right? 3 Earths could fit across the dark spot in that. Okay? So it looks small, it is not. All right? Next slide, Jason. Okay, so let's talk about stars in general so we can understand where the sun is. They classify stars by their surface temperature and their intrinsic luminosity. This chart, if you look across the bottom, is a temperature scale with low on the right, high on the left. Bottom is how bright it is, low on the bottom, high on the top. 90% of the stars live in that, what they call the main sequence of stars that you see in the middle of that graph. The sun, our sun, happens to be almost in the middle of all of that, right? It's an average size, average brightness star. The very big ones are up on the top right, giant. And when I say giant, I mean giant. And we'll look at some of that in just a second. And then some of the smaller ones are on the bottom left over here, okay? So those are all out there. They're not all like the sun. The sun just happens to be a general average star for the most part, okay? Next slide, Jason. Again, I said they're various sizes, and it varies tremendously from size. So I just found this graph. It was one of the better ones to show you kind of the breadth and depth of how big and how small they are. There is a smallness, a lower end, right? If we'll explain in a second. If you don't have enough mass, it's not going to be a star. It'll be something like a Jupiter, like a big planet, right? And I'll explain why. And then you have the really, 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 really big ones that our whole solar system would fit inside them, right? Okay? Next. So depending on the actual size of the star, it determines what it's going to end up in its life being like, how it's going to end its life, right? The theory is there's a bunch of gas out there. It comes together over time. Enough of it gets together, it turns into a star. I'll explain how in a minute. If it's really big star, it will travel down that bottom path. It will become a giant, regular large star. It will live a life down that path for a while, burn up all its fuel, go into a red supergiant, and then eventually either supernova and turn into a neutron star, or if it's heavy enough, it'll go into a black hole. I'm not going to explain to you what black holes are. Nobody really knows anyway, so it's just a bunch of conjecture and theory. We do know that when they collapse into something. and nobody knows why, right? If it goes along the top one, it doesn't have quite as much mass. So when it explodes, it runs out of fuel and then eventually explodes. It does that planetary nebula thing. And I showed 2 of those last week, if you remember, right? What happens is the star uses all its fuel up and all of a sudden collapses. When the fuel runs out, it just collapses into a big boom and it explodes out. And it blows off all the rest of that stuff, right? And then what's left is the white dwarf at the center. So it's a cinder of a star. And those things will eventually, given enough time, spin down, cool off, and just be left as a cinder. But the universe isn't old enough yet for many of those to be around, right? That takes a long time. Okay, so that's a life of a star. And it's measured in billions of years, typically. If it doesn't make all the way to a black hole, it becomes a neutron star. Neutron stars are interesting because they're almost the exact mass of an atom nucleus at the size of a star, which is very, very dense.
Which path will our sun take?
Our sun will go to the white dwarf eventually. It's getting hotter, and it'll get hotter and get hotter. It'll burn out all its fuel. It will go into that giant, red giant stage. It will expand out to just beyond where Earth is now. Then it will collapse and blow off all that stuff. Not very much. Nothing you have to worry about, or I have to worry about. Okay? Okay, Jason. All right, another important thing again, a lot of this points to this argument of the finely tuned universe that is made specifically for us, and this is one of those things. This chart across the bottom is wavelength of light, of radiation, right? From very small on the left all the way out on the right. It goes from ultraviolet, visible, to infrared, and out beyond to radio waves, okay? Top is the intensity. These are called black body curves, if you ever hear somebody talk about them. But in any event, the temperature of whatever object is will radiate according to that curve. So wherever the max point on that curve is, like the 2000 K, that's 2000 degrees Kelvin. Kelvin is an absolute temperature scale going from 0 to however hot you can get, right? It's not like Celsius where you have 0, that's freezing, and then it goes negative. Kelvin doesn't have negative. It goes from 0 all the way up. 0 degrees is 273 Kelvin, just to kind of give you an idea, right? So at 2000 degrees, that star is going to put out its max intensity at about, a 1.25-ish wavelength. And those are micrometers that are really tiny. But anyway, our sun, it lives at about 5,800 degrees. So it puts out its maximum intensity at the yellow-green wavelength. We're a yellow star for this reason. Just so happens to fall right in the visible band that we all use, right in the middle, right? Stuff on that side is infrared, heat, we feel it. You can see it with certain cameras, but you can't see it with your eye. On the left is the ultraviolet side. You'll notice on the far left side, it doesn't go all the way to 0. So the Big Bang Theory side says that the universe was dark when it first came into being because it was so hot it was opaque to light. They didn't have it. And then it came on. And if you look at the creation story, things were made, and then it got light. So there's some symmetry there. But it's an interesting thing when you start looking at it, why this curve is the way it is, from a physics perspective. Okay, Jason. Need to give you, again, let's set our expectations here. This is the size of the sun compared to the Earth. Right? It is 99.98% of the mass of our solar system is in the sun. The other 0.01% is in Jupiter, and we are all the rest. Okay? So we're effectively a speck compared to the sun. It's 93 million miles away. It takes the light, when it leaves there, about 8.5 minutes to get here. Okay, so it's a couple of light minutes. A couple of light minutes away. Okay, Jason. Again, I want to emphasize sizes. On the left is the sun with the planets. Earth is that real tiny one down there. Let me get my cat meowing pointer. Make sure I get the right one. Earth is right down there, right? This is a blown up area of this planet. So you can see how small it is. The sun is gigantic. And it's a relatively small star, right? Okay, Jason. All right, don't start it yet. So I want to explain what this is. You're going to see Mercury transit in front of the sun, right? The planet Mercury, we just saw on the picture. Keep in mind, it's 32 million miles closer than the sun is. Meaning its orbit is 32 million miles off the sun. If it was actually at the sun's surface, you probably wouldn't see it at all, right? Again, I wanted to give you the size perspective. Okay, Jason. See it? See it moving across there? Play it one more time, Jason. I want you to just understand what we're seeing here. Again, there, you see it? That's how big our star is. Yes, ma'am. So I actually meant to look that up. I didn't. It's faster than real time. Mercury's year is 84 days, right? So you can do it's pretty fast, but not that fast. Okay, Jason? So let's talk about what really is happening here. And this is it's an improbable thing. So 75% of all the is in the universe that we know of is hydrogen, the most simple element, one proton. And if it has an electron, it's not too hot. If it's hot and then something like this, it goes away. But 75% of it's that. Gravity starts pulling all these hydrogen atoms in, right? There was some non-uniform field. Gravity starts pulling it in. Eventually, over time, you get the amount that we saw on our sun, or something close to it. Those atoms repel each other because they're positively charged, right, electromagnetically. So they don't want to be near each other. Gravity crushes them, and it makes it hot, and they just don't like it. They don't like their neighbors. They're jiggling all around. They're pressing and pressing and pressing. Gravity gets more and more and more as more atoms join the party. Squishes them down towards the center of the star, or soon-to-be star. Something amazing happens. The pressure and heat make the two atoms hit just right so that they don't bounce off each other, have just the right energy, and the two atoms overcome what's called the strong nuclear force and fuse into one. and a new element is born. Never before been there. The new element is helium, the second element on the periodic table. We didn't even know about helium until the 1860s, 1862, 68, when somebody was watching an eclipse. They got a spectral analysis of the light. They're like, this one, we don't know what this is. It's a brand new element. They named it helium because they found it in the sun. We had never seen it on Earth. This new element, if you weighed it beside the two hydrogens that went in, it's actually lighter than the two hydrogens that made it. It's lighter by 0.7 tenths of a percent. And that 0.7 tenths of a percent of matter disappeared and became energy. And Einstein figured it out. How and to what amount? In his famous equation, energy equals the mass that went away times the speed of light squared. The mass is tiny. The speed of light squared is pretty big. You throw a trillion of them together and you get a star. A star is actual alchemy. It is creating from something like a small hydrogen atom a completely new element. It doesn't, the hydrogen atom, small, you can't contain it, it's very light, it will react with everything. The helium atom is the first noble gas, very stable. And it only occurred in the sun or in other stars initially, before it got out. Go ahead, Jason. So that's what happens. Now, it's a little more complicated than that, obviously. There are some steps and stuff that go in there. But in the end, you end up, you took two hydrogens. They're no longer two hydrogens. They have become one. And they become a different thing altogether. Right? Yeah.
How do you capture helium?
How do you what?
Capture helium.
I don't know how they do it on Earth. But they've had it. You can go get it and blow up your balloons. I don't know the physical process they go through. But the helium, you remember I went through, so this is part of the story though. It was all in the sun. Right? It doesn't just convert hydrogen to helium. Once a star runs out of that, if it's heavy enough, it will start converting helium to maybe lithium or carbon or oxygen, right? And this is important because in the early universe, when they look back, they don't see anything but hydrogen and helium. So where did all this other stuff, carbon, oxygen, and all that come from? Well, they fuse it inside the center of a star. And then when it explodes, all the heavy elements come out. Our star is a type 2 star. It already has some of the heavy elements in there. So the theory is our star is a second generation star. Right? Same process, different elements, different energies, different requirements. Okay, Jason. Our sun is an uncontained, free-running thermonuclear reactor. All stars are. If it weren't for stars, it would be a cold, dark universe. And we'd only have hydrogen and a little bit of helium. So not only does he give us light with these things, he produces everything you need for life with these things. And protects us from it, which we'll get to in a minute. Because that's a violent place. It is not healthy for you, right? Okay, next slide. And again, this is important. Probably most everybody's seen a periodic table at some time in their life. top left, hydrogen, 1 proton, is fused over to helium, a noble gas, first noble gas. And then as the star starts doing its fusion thing, it'll work down the periodic table. I think the heaviest, they say, is nickel or something. Some stars can get all the way up to there. But that's amazing. I mean, you're creating things in the middle of this star that are then blown out into the universe. The rest of the periodic table happens during the nova or the supernova. Because it's so violent, you can get the atomic reactions you can't get in the normal star itself, right? So the fusion process can get you part of the way into this table. It's the nova that could get you the rest of the way, because it's just so violent when they explode. Okay? All right, Jason. So that's a valid question. What's our gas mileage we get off of a star, right? How long does it last? All right, Jason. Every second, you are transmuting hydrogen into helium at a rate of 4.2 million metric tons a second in the middle of that star, our star. Okay, Jason. Over the course of about 4 billion years that the star is supposed to have been alive, it converted the mass of Saturn into energy. So our gas mileage, go ahead, you get about 1/4 of a Saturn per billion years. so we got an extra Saturn, so we got another billion years, right? So we're good. We're good for a while. You don't have to worry. Okay, next one. Oh, by the way, this is an ultraviolet image of the ultraviolet light coming off the sun. There's a lot more going on here, and we'll get into it now. Go ahead, Jason. The sun is not solid like a planet. It's a plasma, technically, but it acts a lot like a liquid. So when it's rotating just like the Earth is on its axis about once every 27 days. Because it's not solid, the equatorial region actually spins faster than the polar regions. Okay, same thing happens on Saturn and the gas giants and Jupiter. Okay, go ahead. The sun, since it is a plasma, has a magnetic field, a strong magnetic field. Go ahead, Jason. And go ahead, one more. This creates a significant problem. You have the magnetic field on the left, North Pole up top, South Pole at the bottom, well behaved. Now you start spinning the middle faster than the sides. And you start distorting that magnetic field around the sun. You're winding up a spring, basically. Okay, Jason? You wound it up. Then every 11 years, the polarity changes on the sun. North Pole becomes South Pole. Now you've got a wound up spring. Go ahead, Jason. Your sun is happy, and then you change everything. And all that energy has been wound up in that magnetic field. And it becomes a very happy sun to a very not happy sun. Right? Go ahead, Jason. You can't hardly see it on this picture. You go from a nice clean sun to all the sunspots. Teenage sun. Right? Next one, Jason. This happens every 11 years, right? And we've been tracking this since the 1800s. We're just finished up solar cycle, well, we just passed the peak of solar cycle 25, actually. So the sun is starting to get quiet again, although this past month has been extremely busy. But there's also usually double peaks. But that chart there, you can't see it there, but each one of those is a solar cycle. And they, like I said, they've been keeping records of these sunspots on the sun going back since they started watching it regularly and keeping records in the early 1800s, I guess it was. Okay? So this is nothing new. So every 22 years, the sun gets back to where it was before. North Pole up top, unwound, and then it starts winding itself back up again. All right? This causes some issues. Go ahead, Jason. Go ahead. So you got a lot of energy, got a lot of heat, got a lot of magnetic fields that have just been switched. What could possibly go wrong when you got that much energy stored up, right? Go ahead, Jason. Well, you get very violent things happen on the sun, and I'm going to show you some of them. Now, when I say very violent, I will caveat this to say that our sun is very well behaved as suns go, as stars go. Some of them are very, very unpredictable. Some of them are very energetic, and we could not live around them. They're unhappy stars. Ours seems to be a very happy star. Okay? Go ahead, Jason. We get to something called space weather. All right, go ahead. So there's a lot here. But I just want to hit some of the high points, and I'll show you some of them. You get, one, the solar wind is always coming off the sun. But when you have those coronal holes, like I showed you on the picture of the dark spots, those are when the magnetic field lets the stuff out of the sun more vigorously. That comes and interacts with our atmosphere in strange and unusual ways, right? That's the coronal holes. You have solar flares, which are usually X-ray radiation that comes, and those typically mess up our shortwave radios and stuff. When you hear about a radio blackout, it's probably usually from these guys. And you have the coronal mass ejections where it just blows out lots and lots of stuff into the universe, into the solar system, right? Fortunately from us, we have a force field that protects us for the most time. Well, we have two of them actually. The first one is the magnetic field that our planet has. That these are charged particles coming off the sun, so they get caught in that magnetic field and shunted around typically. The ones that don't usually end up going in at the poles, and you see those as auroras, right? The other shield is the actual atmosphere itself, which soaks up a lot of the X-rays and higher energy stuff, okay? Without those two, we'd be a lot like Mars. It'd be very unhealthy for us, okay? So let's look at some of them. Jason, go ahead. Again, we'll do solar wind, solar flares, and coronal mass ejections in that order. So go ahead, Jason. So this is solar wind. I showed this, I think, the first day. Again, this is taken during a solar eclipse, so the moon is hiding the brightness of the sun, essentially. And they take these special cameras, and you can see the fields and stuff coming off the sun. That is just going out into the solar system, right? It's just beautiful. Okay, so that's the solar wind. Again, that one's not typically dangerous to most of the stuff that we do. If your planet doesn't have a nice force field around it, it tends to strip away your atmosphere, right? So it can do some damage. Next one, Jason. All right, this is solar flares. These are just high energy radiations. When these magnetic fields collapse and recombine, it's just like a slingshot, and it's just very, very energetic. And we'll show one now. Go ahead, Jason. I hope this plays. Yeah, all right. So this is one. By the left side, you'll see it in a second. Boom. Did you see it? That bright light? All that energy just flashed out. Go ahead and play it again, Jason. What you don't see is that it's an X-ray event. Very highly energetic radiation. just explodes all of a sudden off the surface of the sun. Okay? Okay, Jason, you can go to the next one. So don't play it yet, Jason. So this is coronal mass ejection. So this is where it's going to just blow out matter into space, right? A prominence there is the dark thing. It's about the mass of Mount Everest, but it's spread very, very thin. The Earth would fit under that nicely, easily, right? You got to remember the size of these things. Okay? All right, Jason, play it. Boom. And the magnetic field just flings it out. And if you're in the path of that, you have some problems with satellites and electrical grids and stuff, depending on how strong it is. Okay, play it one more time, Jason. It's fascinating. You can see the magnetic loops. So there's plasma flowing back and forth around those loops. That's why you can see them. And then whatever happens here underneath the surface just releases that one. And it just flings it out into space. Right? Very hot. Okay, Jason. All right, these are cool instruments. So this is a coronagraph. It's out on the weather satellite that's in geostationary orbit. So it's 22,000 miles out, and its orbit speed is exactly matched with the rotation of the Earth. So from us, if you were to look at it, it doesn't look like it ever moves. It sits right over us, right? It's at the equator. And so what they do is they put these little, it's almost like putting your thumb up in front of a telescope in front of the star, in front of our sun. The little circle in the middle of that is really where the sun is, right? The little circle there. And what you're seeing is the one on the left just now released a coronal mass ejection. You can see it go out. Watch. Here it comes. Boom. See it? Blowing off to the left-hand side. You can also see a comet on the bottom left, coming from the bottom left. Yeah, just happened to catch one that day. One on the right-hand side, it's a big one, and you can tell it's probably either more aligned with coming at us or going away. You can't tell just from the picture. You have to have some measurements on the Doppler shift of it. Is it going to us or going away? But that one looks like it's coming to us. And you can also see the moon. That's what that big bright flash is that went in front of it, right? Because it's out there rotating too. And so this is out there 24/7. You can go look at it any time on the NOAA website, for the Space Weather website, and watch the sun, right? Beautiful. Okay, Jason. So yeah. Did somebody have a question? No. Okay. So we actually just put out a satellite that is the closest man-made object we've ever put out to orbit the sun. It's called the Parker Solar Probe. It got within 4 million miles of the surface of the sun, which is effectively on the sun, in the atmosphere of the sun anyway. That's it. It's not too much bigger than the size of that board, that black kind of thing that's facing the sun that keeps the heat off the actual instruments and stuff. So it's not a huge satellite, and it has cameras that look over the edge. And on the right-hand side, you'll see some of the images it took as it went through. And I'm going to show you an actual movie of it in just a second. So you'll see the mass blowing off the sun. You'll also see a lot of lines in the screen. Those are not real. That's radiation hitting the instrument itself, and it flashes the CRT. You'll see it. You'll see what I'm talking about in a second. Okay, go ahead, Jason. And it should play. You can check it and see if it'll go. Yeah, there we go. So that's it, as it's going around the sun, getting it up close and personal. And go ahead and play it again, and you see all the lines. That's not particles. That's not healthy radiation that the instrument has to deal with. Inside the atmosphere of the sun. Cool. Very, very cool. Yeah, so I got it, a year ago, this week, actually. I sat at the table with the guy who designed this spacecraft. And he showed for the first time one of these movies like this. It was fascinating. Much longer than I was able to get, actually. But and they had some audio as well. It's just, you can't believe that there's an instrument that would survive that, honestly. But it did. They engineered it well. Okay, Jason.
So what is the shield made out of that protects it?
It's kind of like the space shuttle shield, if you recall, that ceramics. Yeah. And so they have that, and then they have a blanket of kind of like a wool stuff, and then I think it's aluminum substrate after that. So it's kind of a layered thing. And they have some instruments that are able to look around it and to the side. So it's fascinating, really. There's a lot of effects, and I'm not going to go into a whole lot of them here because I do need to kind of round it out. And I want to do it this way. I didn't get a chance to talk much at all about some small things, and in particular, some biology, right? One, it's not my field. We just don't have time. I would cover some of it next week if I had a chance. But I do want to just talk about some things and the amazing, truly amazing things. And it goes back to the sun. All the energy that we use, all of it, comes from the sun. 99.9999%. The only small amount of energy we are able to tap into that doesn't come directly from the sun is radioactive decay energy inside the planet itself. So some geothermal stuff, right? Everything else comes from the sun. You need to realize that. Without it, we don't survive. That's how important it is. This sweet goodness is maple syrup, right? Absolutely love it. There is this machine that turns this dirt, regular dirt, into that sweet goodness. This into this. And it's at the bottom of roots on a maple tree. And that maple tree takes this, makes this, lifts up about 1,500 pounds of it 20 feet in the air without a moving part. It then takes this, if I don't eat it, it takes this and grows leaves. And those leaves take this material, capture sunlight, takes in some carbon dioxide, and captures that energy from the sun that left 8.5 minutes ago, stores it, pumps it back down into the roots to start all over again. Sunlight. There's a machine that does that for us. Gives us shade, gives us sweet goodness. In the fall, it gives us beautiful leaves. You cut it down, it's a battery. When you burn wood, you're just releasing the energy that it stored from the sun. That's all you're doing. So it's a battery. also be a table. It's also potentially the most rare thing in the universe. We can look out at the stars and see gold, platinum, rubies, and diamond, titanium. There's no indication that there's anything else like that. Are you kidding me? There is nothing, this could be the rarest thing in the universe, and he lets us live with it daily. We can make diamonds, we can make pearls, we can make anything we want. We even have wood satellites, by the way, in case you were wondering. We can't make this. So, in the end, I guess he made the sun and all that so that at the end of the day, in the cool of the garden, he can walk with us in his creation. It's a love story. What else could it be? This is a beautiful thing. It's an amazing thing. Phenomenal that there are things out there that can do that. You don't have to look to the stars. You can, because this is star matter. But it's phenomenal. And so I want to close, and I hope that, I guess I will consider myself successful if at some point during your day you look and are in awe and go, God made that and he loves me because I get to enjoy it. Does anybody have any questions before I turn it over to the preacher? No? Thank you. Yes, ma'am.
Could we mine any of those things?
Oh, absolutely. They're out there in the asteroids. They're not even far away. Did somebody else have a question? Yes, sir. Well, there's.
John, I've always heard of solar flares being a potential end of our civilization, kills all the computers in cars and everything. Speak to that.
Yeah. So, and Jason, if you'll just go ahead, I was going to talk to it a little bit. Just go ahead one slide maybe. Yeah, so end of civilization, I don't know. I doubt it because we've thought about this for a long time. It could set us back a long way though, for a long time. There's been events that were so powerful, they caught transmission lines on fire, right? Long term, this is a problem for satellites, especially the low Earth orbit ones, right? It will expand our atmosphere, which will cause a lot of drag, which will bring down all those satellites, right? Or the satellites will maneuver to get above the drag and bump into each other, and then you start a cascade effect. That's what the military worries about now, most of all, is something like that. Because the satellites are autonomous now. They sense that the atmosphere drag is above what it should be, and they start maneuvering. And that's a problem.
So can they predict that now?
We can predict it a little while. Once we see it, sometimes you have a day or so before it gets here. Yeah.
That's when you have the Faraday box and you put...
Yes, yeah. But fortunately, our magnetic field and the atmosphere does most of the work for us. It's really strong ones that we have to look out for. And it could be a really bad time. It could be. But it won't be civilizational ending, I don't think. Sir, did you have a question?
You know, we hear a lot lately about global warming being man-made. But seeing that big flare come out of the sun, that looks like that's more than any man could make.
Yeah,
What's the
so
relationship between sun flares and sun activity and global warming?
so there's research to support that the sun may be part of it. And it certainly is getting warm. The sun is getting stronger, right? We can measure that, but it's small. The real problem with saying that is the complicated system that it is. This is just one profile of the atmosphere. You have ozone, the temperature graph, which is the yellow one. The reason it goes up after the troposphere, stratosphere, is the ozone stuff. If that changes, does it get lower into the atmosphere? It is phenomenally complicated. So this is why I get on people who say, well, it is man-made. Because they don't, from a science perspective, they can't say within the error bars what the top of the atmosphere amount of radiation that you're talking about is compared to how much is changing. So what I'm saying is, how do I explain this? The error bars in what we know coming in are bigger than it would take to make your argument for global warming, right? Because of that. So it's just it's irrelevant to make that from a science perspective. Now you can argue it a lot of other ways, and people often do, but I'm telling you, I do atmospheric modeling. The system is so very complicated that you can't just turn a couple of knobs and go, yeah, this is going to cause runaway global warming, right? It may. I can't say that it won't, but you can't say either from a science perspective that it will, right? Very complicated. Yeah.
Johnny, when we were in Africa together, you spoke about how remarkably Earth is protected by the solar system and the sun and even belts of asteroids from radiation that comes from galaxies and other stars and
Yep.
even from our own. Could you speak a little bit about that?
Yeah, so again, this goes through the fine-tuned argument, right? So that sun is a violent place. It puts out X-rays, it puts out alpha particles, it puts out gamma rays. The Earth has a giant nickel and iron core that rotates, and it's a magnet. And the magnetic field surrounds us. The radiation comes in, and most of it gets caught in that magnetic field and goes around the planet, right? Well, the galaxy is producing even stronger radiation, but fortunately the sun, we just showed all those magnetic field lines, produces that and shoots that out, and so that protects us as well. The big planets, particularly Jupiter, scoops up all the asteroids. And if you, remember if I showed the orbits L2, L3, so in L1, 2, 3, and 4, Jupiter has, it's an enormous amount of asteroids that get caught in that null area and don't make it into the inner solar system, right? That protects us. So there's four fundamental forces that we know of in nature: gravity, electromagnetism, weak nuclear force, and strong nuclear force. If they aren't perfectly balanced, you don't get a sun. If the gravity's not strong enough, it won't pull it hard enough to combine them. If it's not strong enough, if the strong nuclear force is too strong, they can't combine. If it's too weak, it happens too fast. And then in a weak nuclear force, which is a process internal to the atom itself, which deals with neutrons and protons. If it's off, that's the real one, where they say if it's off even, tiny bit, you don't get radiation, radioactive decays or fusion. So if those four are not in perfect balance, you don't get a star. If you don't get a star, you don't get light, you don't get the heavier elements, you don't get anything. That's why I say it's the most improbable thing of all. It has to be perfect.
Fine-tuned that it gives the place for the one planet that we can see anywhere
Yeah.
to have life on,
Yeah.
sustain.
From the very simplest of things, hydrogen. If it all doesn't come together correctly, you don't get any of it, right? Any of it, anywhere. Yeah.
How do astrophysicists explain the coalescence of stars? I mean, in our experience, most clouds dissipate. Most matter just blows away with random action and never dissipates around a core. How do they explain there being a sufficient concentration of matter to begin exerting a uniform gravitational pull toward a shared center?
Yeah, so the theory is that small perturbations in essentially a fluid like that will mean that gravity is strong enough. Sometimes gravity is strong enough that it will start coalescing things close to them, right? If there's a strong wind or whatever, like we saw that nebula going out, so you won't get one there, but eventually that stuff will slow down. And gravity, the force of gravity is infinite. It's reach, not its force, but its reach. So at some point it's going to come back together, right? And this is the argument they're having about, well, is the Big Bang Theory true or not? Because this expansion thing, if it's too fast, you don't get them ever coming back together, or at least not enough. So you got to have, it can't be completely homogeneous. You have to have some bubbles here and there where it can just start. And then once it starts, even if it's tiny, once it starts, it's going to start pulling in the rest of the stuff.
So if you have, I guess, like two hydrogen atoms just orbiting each other, eventually they'll pick up a third and a fourth.
Exactly.
That makes sense.
Exactly. Yeah. Again, tuned correctly. Okay. Anybody else? Well, thank you, everybody. I really appreciate it. I hope you get something out of it. I hope you remember it. If you ever have any questions, I'd be glad to chat with you. Over to you, sir. Thank you.
How many of you guys are satisfied that this is the end? You know, it's when you look at the Bible deals with material existence. We're these spiritual beings that are invisible, but we're put into these bodies. These spiritual body, these physical bodies are our reality. And that should mean that we should be very concerned about our material existence, the world around us, and to care for it, and to love it, and to have awe in the midst of it. And Johnny, you've given us just a great little appetizer, aperitif, sherry, whatever you want to call it, a wonderful beginning of sort of evoking that awe that we should all have. And Johnny, you know, you have your own life, you have your own ministry and calling, and I just have a feeling that you're going to be back to this. You're going to be back to us. You may even be back to some other churches. And I think this is something that people want to hear, isn't it? Don't you want to kind of know a little bit more about the world that you live in, about the majesty of its creation, and also just maybe not look at scientists as, you know, opponents. Scientists deal in the marvelous existence of our reality in ways that we often don't. And this is to be commended, and this is to be honored. And we're very grateful that you took the time to share that with us. So thank you so much, Johnny. One more time, a round of applause, and I'll close in a word of prayer. Let's stand together, and why don't we close in the Lord's Prayer together. Our Father, who art in heaven, hallowed be thy name. Thy kingdom come, thy will be done, on earth as it is in heaven. Give us this day our daily bread, and forgive us our debts, as we forgive our debtors. And lead us not into temptation, but deliver us from evil. For thine is the kingdom, and the power, and the glory, forever. Amen. Isn't it interesting how the Lord's Prayer kind of summarizes everything we just talked about? Maybe think about the way that our spirituality and our biology go together. Thank you guys so much for coming.